Hey guys, how's it going? I hope you're ready for this because this is going to be a lot. Today we're talking about KVL and AC, starting with KVL. So, Kirchhoff's law is one of the two circuit equalities described by the German physicist Gustav Kirchhoff in 1845 to account for the current and potential differences in the lumped element model of electrical circuits, which assumes all the components of a physical system can be concentrated to points with ideal mathematical behaviors, as is done in any basic circuit diagram, such as the one here. It states that the sum of the voltages around a closed loop is zero, which makes sense given energy must be conserved. And as KVL is an essential corollary of Maxwell's equations, you can see one of the derivations here. It can be applied to alternating currents. However, there is a lower frequency limit as KVL assumes a constant magnetic field, so if the frequency is high enough that the field is constantly collapsing and cannot stabilize, meaning the current is constantly changing and the magnetic field as a result, or the current operates over a distance long enough that the change in polarity through the wires is distributed and propagates rather than being instantaneous, which additionally introduces other effects such as reflection, which must be considered, then KVL fails. Now let's define AC. AC is a current that changes polarity or direction and can be defined through the superposition of sinusoidal waveforms, but is often inherently sinusoidal as a result of its common generation via rotational action, such as in generators. We can relate this rotational action to the waveform by the angular velocity, which considers the rate of change in angle over the change in time, and this is directly related to the period of the waveform, and thus its frequency, speed, and wavelength, which can be seen by the white text and is also represented by the graph. And thus the components' responses can therefore be related directly through their amplitudes, noting that the frequency affects the phase of certain components with non-constant differential reactances, which can be derived, as is done here, by considering the way the current changes with time, such as how current is dependent on the change in voltage for capacitors, as when they are fully charged, no current flows through them. To employ KVL, it's more convenient to use polar and rectangular forms as the frequency is constant in both parallel and series circuits, and it's easier to operate on phasors. Phasors are the vector form of the sinusoidal function comprising the magnitude and direction, where a complex number represents the imaginary components of the current derived from the stored energy in capacitors and inductors, which influence the phase. By convention, the RMS value is used, which is displayed here, but we won't be using this. And here you can also see the two different forms, their benefits, and the transformations between the two. It is important to note that due to the opposing nature of inductors and capacitors, the J is negative in series for capacitors, giving it an angle of negative 90 degrees as opposed to the inductor's positive 90 degrees. And here we have a final example where we have converted the E to polar form, found the reactances and the total impedance in rectangular form and converted it to polar form, used Ohm's law to find the current and the individual voltages and then added them together in accordance with KVL, and then we've converted back to rectangular form to add them and back to polar form to find that the sum of all the voltages in the closed loop is equal to the source voltage, proving AC application of Ohm's law. That is all up. So yeah, end. And yes, this faulty slide that's intentional. Yeah, yeah, that's intentional. Yeah, I just wanted to add a bit of character to my presentation. I didn't start this PowerPoint presentation and then realize that the very last frame is off.